How much energy? This is going to be a bit of a marathon problem. How much energy does it take to convert 0.50 kilograms of ice at negative 25 degrees Celsius? So we're starting with a block of ice at negative 25 degrees Celsius to steam at 220 degrees Celsius. So we're going to take a 0.5 kilogram block of ice. We're going to keep adding heat to it. We want to know how much energy will convert all of that at 25 degrees Celsius to start, all the way to steam that is carrying a temperature of 220 degrees Celsius. How much energy do I have to put into it? We have to do this in 5 steps. We have to account for this step, the rise in temperature of the ice, the melting of the ice, the rise in temperature of the liquid, the vaporization of the liquid, the rise in temperature of the vapor. We have 5 calculations to make. So let's get going. Okay. Now we have some information here. We have the heat capacity of ice is given to us. That is equal to 2.1 joules per gram per degree Celsius. We have the heat capacity of liquid water. I'll just say C of liquid. You know what? I'll just say C of water. How's that? C of H2O is equal to 4.18 joules per gram per degree Celsius. You know that from our work in thermochemistry. And as it turns out, the heat capacity of steam is 1.8 joules per gram per degree Celsius. The heat of vaporization of water is equal to 40.7 kilojoules per mole. And our last bit of information, the heat of fusion of water is equal to 6.0 kilojoules per mole. This was actually kind of a surprise to me. 6 kilojoules doesn't seem very much, but it's still, 6,000 joules is still kind of a lot. Okay, so let's quickly draw our picture again so we have something to reference. I'll actually make it kind of small just so we have a pictorial. So I'm going to draw my picture over here. So again, we're looking at something like this. 1, 2, 3, 4, 5. We have 5 calculations to make. So let's start. From minus 25 degrees Celsius all the way to 0 degrees Celsius, we're going to use Q equals mc delta T. We're putting heat into something. It's going to equal that heat capacity equation, Q equals mc delta T, the mass times the heat capacity times the change in temperature. Okay, because they're asking for how much energy. So Q equals mc delta T. Well, that's equal to, the mass is 500 grams, right? 0.5 kilograms, times, well, this is ice, so it is 2.1 joules per gram per degree Celsius, times the change in temperature. The change in temperature, 25 degrees to 0, this is 25 degrees Celsius. When we calculate this, we get 26,250 joules. That's our first calculation. It takes 26,250 joules to convert 0.5 kilograms of ice to raise the temperature to 0 degrees Celsius. We haven't actually converted it yet. Now, at 0 degrees Celsius, 0 degrees, ice, we want to convert that to water at 0 degrees. So here's where we're actually going to convert it. We're going to melt it. This is where we go. Well, we have 500 grams times 1 mole equals 18 grams, right? 1 mole of water is 18 grams. And we have the heat of fusion of water is 6 kilojoules per mole. So 6,000 joules per mole. Gram, mole, mole, gram, gram. When I do that, I get 166,667 joules. That is the second part. This is the first part. This is the second part. So it takes 26,250 joules to raise the temperature of ice from negative 25 to 0. At 0, it takes an additional 166,667 joules to melt that ice to convert it into liquid water. Now we need to raise the temperature of water from 0 to 100. So that calculation looks like this. So we have 0 degrees Celsius to 100 degrees Celsius. Again, we go back to the Q equals mc delta T, except now we're going to use the heat capacity 4.18 because now we're talking about a liquid. It equals, again, 500 grams of water. That hasn't changed. 4.18 joules per gram per degree Celsius. And this time, our temperature change, 0 to 100, is 100 degrees Celsius. And we end up with 209,000 joules. Now it takes 209,000 joules to raise the temperature of water from 0 degrees Celsius to 100 degrees Celsius. That was the third phase. Now we need to add enough heat to actually change all of that liquid water to gas. This is going to be the fourth phase. So at 100 degrees Celsius, we have water, and we need to convert that to steam at 100 degrees Celsius. Notice the temperature stays the same until everything is converted. Once again, we have 500 grams. Well, 1 mole happens to be 18 grams, so that is the mole conversion. And the heat of vaporization is 40,700 joules per mole. That means 1,130,555 joules are necessary to actually change 500 grams of water to 500 grams of steam. That is a hell of a lot of energy. I'm telling you, hydrogen bonding, profoundly strong. Now, we need to take steam from 100 degrees Celsius all the way to 220 degrees Celsius. We go back to Q equals mc delta T. We have, well, mass, again, we still have 500 grams. This time it's of steam. It's 1.8, I'm sorry. The heat capacity of steam is 1.8 joule per gram per degree Celsius. And this time we're raising it 120 degrees, right? 100 to 220 is 120. And we end up with 108,000 joules. Now we have to add all of this together, the 108, the 1 million, the 209, the 167, the everything else. When we add it up, we get 1,640,472 joules, or 1.6 times 10 to the 6 joules, megajoules. That is our final answer. So the moral of the story is, if you're changing phases, you have to account for the phases themselves. If you're going from solid to liquid, you have to take care of the rise in temperature of the solid. You have to take care of the change of the solid to liquid, and then the rise in temperature of the liquid. Or if you're going the other way around, if you're taking liquid to solid, the drop in temperature of the liquid, the conversion of the liquid to solid, and the drop in temperature of the solid. You have to consider each phase. Think about the heating curve. Every segment of the heating curve, that's what you have to account for. On the places where temperature rises, you use Q equals mc delta T, heat capacity of the particular phase, and on those places where the temperature is constant, you use the heat of vaporization or the heat of fusion. I hope that helps. Okay, thank you for joining us here at Educator.com to discuss changes of state. We'll see you next time. Bye-bye.